Good afternoon, everyone. Welcome to this session focused on AI4EO, advancing Earth intelligence through AI and Earth observation. So in this session, we have several speakers. Professor Keshev from University of Cambridge, Department of Computer Science and Technology. We have Andrea Nassetti from KTH, Professor Davis Tuya from EPFL, and we have Steve Kopp. Do I say Shop or Kopp? From S3. So we will have another panelist who join in the end at the panel discussion. Torsten Jelinek is working with AI governance. I thought if you have questions on that, he can answer as well. So yeah, we have a very exciting panel from foundation models to application examples to agentic AI to benchmarking foundation models, so diverse of activities and topics. I think those are really the cutting edge of AI at the moment. Hopefully you will also learn a little bit about the AI4EO working group, or we call it enablers activity. So I'll start with that. We were established last year as an enabler, cross-cutting enabler by GL. Before that, we were an ad hoc working group, and there was quite a big interest in this. So the goal of the group is to strengthen the integration of AI into Earth observation and also accelerate adoption of trustworthy and scalable AI approaches that enhance the GL's activities. We basically want to serve as a cross-disciplinary, cross-sectorial exchange. Here we have, academic partners, industrial partners as well, and knowledge sharing, capacity development, and responsible AI practices. So all these are very important for inclusive Earth intelligence. So we have 4 different subgroups. So if you come here, you're interested, please join us. Now we have about 150 plus members. So this was some time ago, and we also already have 30 originals by that time. So we have 4 different working groups. Data sets, tools, and use cases is the first one. Then we have another working group, workshops, webinars, training initiatives, then policy, law, ethics, and AI governance. That's also important, how to use AI responsibly. And then final group is really being able to write white papers and policy briefs. If you were in the town hall this morning, I talked about a AI4EO white paper. That's like a big book of 240 pages, but we will develop that into a policy brief that can serve to decision makers because they don't have time to read 240 pages of a book. Anyhow, so what we have, some of the key major events we have participated in, we were at the ESA-NASA International Workshop on AI Foundation Models for EO. We were at ITU AI for Good. And this summer, we will be at the ISPRS Congress One Earth Forum, and also being invited to the UNGGIM Academic Networks Forum on implementation of geospatial AI technologies. So there, AI for Good is coming summer. We also have a representation. So there are many activities and events we would like to broaden our connections and impact with the community. And we also organize the webinars. geospatial foundation model. There are many of those. Which one is good and what are they good for? I think Andrea will talk about that specifically, but there was a training workshop on that. And then Professor Keshav has given a talk about Tessera, and he will talk about new development in this session. What's new with Tessera? Then we also have challenges. Andrea will talk about it. I will skip it. So there are a lot of AI models. I think some of you have been using it, and AI4EO is really expanding, evolving, and there are many like acronyms of models around. And so, which one to use? Which model is good for what? What are the advantages and limitations? So that's the motivation for us really to look at. To have a reference or living book so that we take a look at the landscape, what's going on in terms of core technologies, learning paradigms, and also from system perspective, and then find use cases. So what has been useful, and also what are the opportunities, challenges, and what are the how, best practices and how to use AI more responsibly. And we also have policy law governance chapter. So yeah, just want to show here is a living book. So if you scan the QR code, you will have the access to the 240-page book. And apologies for the formatting because I invited authors to write, but I didn't give a template. So they came in different shape and sizes in terms of the formatting. And we just got the last contribution a couple of days ago so that didn't have time to really put everything into one template. So the good thing with the living book is we are always improving. We also want your comments. So there are a number of chapters, and someone talked to me to say, oh, CEOs also have a AI4EO white paper. Have you seen it? I only saw the table of contents a while ago. I don't know if some of you here have seen the whole white paper, the CEOs. I saw some head nodding. But anyway, this one is very different from the table of contents. At the time, I haven't got a full copy of theirs and not ours either. So we have more technology-oriented approach. We surveyed many of the cutting-edge AI models and also gave some general reflections on what are the advantages and limitations. And also we have showcased examples on biodiversity, wetlands, forest monitoring, land degradation monitoring, urban mapping, urbanization monitoring, as well as disaster management. So there are many different things here, and there's a specific chapter on responsible use of AI, trustworthy AI. And so, yeah, so here, basically we conceptualized the core neural network architectures. It's a spatial group CNNs, and then we have sequential temporal models. Then we have the graph networks, neural networks. Then from a learning paradigm perspective, and we have this supervised learning, semi-supervised learning, generative learning, contrastive learning. Then from a system level perspective, then we have foundation models, agentic AI systems, and then there are a bunch of applications of what different models might be good for. I thought this was a surveying of the literature that might be useful for user community to have this information. Yeah, so we identified a bunch of opportunities and challenges. So I think our speakers will talk more about, demonstrate variety of opportunities. And I think really challenges for all of us here, the community, is really how to be mindful of data quality bias and underrepresentation of the global south and limited model generalization, cross-region sensors and contexts. And we need more explainability, uncertainty reporting, and benchmarking, and also reduce the digital divide to have more access to infrastructure for the global south. And definitely how to use AI sustainably. So not everything need to be solved by AI. Some things don't need AI, I would say. So don't use, okay, help me with search, Google search. Maybe you don't need AI for that. And, consider all the computation resources. Yeah, so just want to demonstrate maybe a couple examples from my group's work. Is how AI4EO have been used for 3D urban mapping, cities not growing in 2D, but also 3D. The global, models like the global building atlas is from 2019. It's 7 years old, believe it or not. And also the Google Open Buildings, it's temporal, but it's only for part of the world. And the latest one is not available. So how do we leverage open data, Sentinel 1, Sentinel 2, as well as LiDAR, building height information in some countries and cities in Europe, and train the model and being able to deploy it elsewhere. So this is an example. So we also publish not only the result in the paper, but also the data set and the codes. So it's open and free to use. Another example is how we use generative AI for daily high-resolution wildfire mapping. We could do, actually, the aim is actually to have sub-daily because VIIRS is a few hours later than MODIS and Sentinel-3. So if you can, using pre-fire Sentinel-2 image at 1020 meter resolution, and then the low resolution images at 300, 500 meter resolution, and generate daily high resolution images, that would be super beneficial for the emergency response and situation awareness. So this is another work. And anyway, so I think GL, our community, have a unique role for scaling up the responsible AI for Earth intelligence. We can coordinate open AI ecosystem as, GL Knowledge Hub, open data, open knowledge is already there. And we have the living book, and we also collect data sets and tools. Maybe you heard about it. We talked about it yesterday. So we will put them on the Knowledge Hub. And how to reduce bias and, geographical inequality, basically to, promote representative training data, local validation, more rigorous validation, adaptation across regions, and build trust for end users. A lot of the users, think AI is a black box. How do we build trust? It's also important to demonstrate not just, accuracy numbers, you can show this is detected correctly visually. And enable uptake through guidance and use cases. So that's why I think we have this community here. We provide the living book, we keep on updating it and being a resource for the community. Yeah, thank you very much. So the session, so join us. If you want to join the AI4EO, scan this QR code, and then you can choose the working group, which working group you want to contribute to being part of the community. Yeah, thank you very much. So the plan is we will have speakers presenting continuously. Then we will have, in the end, we have a panel or Q&A session. So please.
Thank you very much, Yuka. I hope you can all hear me. One of the aspects that Yifang identified was enabling uptake of foundation models in use. So I'm going to be talking about the democratizing Earth observation by using foundation models. The Tessera model is the one that I've been working on. I'm going to talk a little bit about what is, from our perspective, the challenge of Earth observation, something about geofoundation models, some design choices that we made, a little bit about Tessera itself, and the tooling we provided to make it accessible for everybody to use. The team is quite large, but I want to highlight actually two people. So Zhangpeng Fang or Frank Fang is the first author of our paper. He's my PhD student. He's been sort of the one-man genius behind all of this, who made this all work. Absolutely brilliant student. You'll be hearing a lot more about him, probably in the headlines of newspapers in the years to come. But for the moment, he's still my student. Soon he'll be my teacher. And Clement Atzberger is the person who thought of the idea of behind Tessera, which is Barlow twins. He's a person working in remote sensing for many decades, and also has the intuitive understanding of AI and has been a remarkable teacher. So he taught me everything about remote sensing. So if I make any mistakes, it's my fault. If I know something, it's because of him. And Maddie Lissay is at the bottom, did a PhD on this topic. I'm going to skip all the others. So the main challenge we see with Earth's observation is something like this. When you look at the Earth, it's not always the same thing. You have clouds, you have changes in lighting, you have atmospheric effects, you have varying time gaps. So the problem is what you're seeing is not very clear. And what people do is they create these composites where they take the best images from a period of a few weeks or a month and create this beautiful image, such as this image of Europe, but it's extremely rare to have a cloud-free Europe. So what's going on is that the temporal signal is being lost, and this temporal signal is critical. What I'm showing on the left is 9 different plant species, and on the y-axis, I'm showing different bands from Sentinel-2. On the x-axis is 3 years. And what you see is that over the period of 3 years, these bands exhibit typical variations temporally, and these variations allow us to distinguish between in one species. This is lost due to composite pattern. Crops, are the ground, the field is brown, it turns green, it gets darker, etc. And so this is basically the signal that's being lost. So what we do with geofoundation models is to basically take the annual sequence of the observations from the first satellite showing in blue on top, and another sequence, like the brown sequence on top, another annual sequence, and convert the entire sequence of these using the model into what we call an embedding. In our case, it's a 128 dimensional embedding. Other foundation models use different values. Some are 1,000, some are 64. It all depends. But the interesting part is this embedding is ready to use. In other words, what we have is for every spot on Earth, every 10 by 10 meters. So this room is approximately 10 by 10 meters. That means we have one embedding, 128 values for this room. And we have one like this for every such spot on Earth, 240 terabytes of data. So what I'm showing over here is for each 10 by 10 meter pixel, 128 bands. And you can view this as if you're seeing the Earth through AI glasses. And for when you see that spot on Earth, what you're going to see is 128 dimensions, not 3. That's the basic idea of a foundation model. Now, we've heard the word foundation model many, many times, but I thought it might be useful to understand how it's made. And I'm going to show you a sequence of about 15 images. Please pay attention, because if you miss even one step, you're going to lose the whole thing, right? So here it is in about 2 minutes, what a foundation model is. And after this, you'll never be confused again. So we start with pre-training. What we do in pre-training is we get a lot of data from different satellites, S1, S2, for example, and we get global data ingestion. We gather all this data, and then we do decimation. We reduce it by a factor of 1,000 or 400, 200, because it's too much data. The global data is typically around 3 to 5 petabytes, a lot of data. Once we get this, we get the spectral temporal data, we gather that, and then we do something called self-supervised learning, or SSL training. What this means is we train an AI without giving any labels. It teaches itself, and that's the beauty of it. I'll show you how that's done. Once you do that, you get what I call model weights. These model weights are the result of training. This is an encapsulation of all the knowledge that has been gained by doing the training. In the second stage, we do what's called embedding generation. And embedding, remember, it's a 128 dimension vector. To get that, we take the same data for the ROI that we care about, and we ingest the data from the ROI, and then we collect this SST data and put it through what's called the inferencing step, where we push the data through the weights and we get the embeddings, right? So so there's two steps, the pre-training, where we're doing this self-supervised learning, and in the second stage, we're creating the embeddings. And then these embeddings are published. The third step, we do task-specific training. So now what we're doing is we're taking the embeddings and using that for a downstream task. So the way we do that, we get the ground truth and environmental variables that are relevant. For example, this could be what crop is growing on a particular field. It could be when a wildfire happened, what is the intensity of the wildfire. It could be the height of a building or the height of a tree. We take these, and in the supervised training, we take those embeddings and the ground truth, and we come up with task-specific training weights, which I'm showing on the right-hand side over here. And finally, we do inferencing for the whole ROI, where we don't actually have the ground truth. So I may know the value of the crops in 10 fields, but I want to know the value for 1 million fields. What we do with foundation models is to amplify your knowledge by just knowing 10 fields of labels or 20 fields of labels, something like that. I can tell you all the crops growing everywhere in your country. So in that step, we take the same environmental variables which are available and the inferencing that we got and the embeddings, and then we make predictions of what's happening. So this, in some sense, is the entire stack. So what choices do we make? First is, where do we get this global data from? Second, how do we do the decimation? How do we, whether we use spectral, spatial, or temporal data? How do we do the training? And how do we make these, the ROI? What is the ROI that you care about? And so for Tessera, we made the following choices. First, we use global data. So we get Sentinel-1 and 2 data from everywhere rather than from single biomes. For our case, we use only spectral, temporal, or pixel-based rather than using spatial. So we don't do spatial, but most other foundation models do spatial. And that gives us some benefits and some negatives. I can talk about that later. For training, we use something called Barlow twins, which I'll show briefly. And for the inferencing, we don't just do a small region, we actually do the whole world. We provide all of the world as inferencing. So those are the choices that we made. And so the architecture looks something like this, and I don't have time to show you exactly what it is, but basically the input data goes through a decimation process and then goes through these two arms, which are the upper and lower arm, which use reduce values from the time series, and you say make it look the same, and this causes the AI to learn how to ignore gaps. And so this idea makes it possible for us to create embeddings which are invariant to cloudiness. And so we can take fairly cloudy regions and still get valid embeddings. And we actually do it for Sentinel-1 and 2. So we have this multi-arm thing, which I can't go into in great detail, but our paper has all the details. What does it look like? If I take the first 3 dimensions and show it in false color, you can see that there's quite a bit of richness. It encapsulates a lot of knowledge. And if you go even further, for example, this is near Vienna, you'll see that the fields have different colors. And it turns out these colors actually are encoding for the crops that are growing there. So we can tell you with high precision what the crops are. We can also see cities, we can see rivers, so we get a quite interesting view over here. The performance is quite good. So we compared it on classification, segmentation, and regression tasks. So 6 tasks that I'm showing over here. The takeaway message is that the big hexagon out there is Tessera, and we compared it with the laundry list of alternative foundation models, and we're outperforming them or matching them. In particular, Google Alpha Earth, which is sort of a similar embeddings and data approach, seems to be, at least on this task, performing close to or not as good as ours, and ours is open. It's completely open, and theirs is not. So I just want to end with giving you some tools that you can use in your work. The Tessera, the left-hand side is the Tessera GitHub repo. You can see everything. You can recreate everything yourself if you want. We have something called GeoTessera, where you can give a bounding box and download for yourself the embeddings for the region. As I showed you, we've done the whole world for 2024. We're working on others. On the right-hand side is a tool called the Tessera Embeddings Explorer, which is at tee.cl.cam.ac.uk, or this QR code. And with that, you can actually see for yourself what it is. I have a demo here I can show you. If you want to use it and you want an account, I'm happy to create an account for you, because I wrote it, rather, I should say, I vibe coded it in the last couple of months. And it's been the most fun I had. And that's why I work in remote sensing. It's the most exciting and fun place to be right now. So thank you very much.
Thank you. Yeah, I think we're going to
The next one, yeah.
Steve.
Okay.
Steve.
Okay. Thank you, Yifeng. Hi, Steve Cope from Esri. I was asked to talk a little bit about agents and assistants. And so the first thing I want to do is provide a little bit of context for agents and assistants with regard to models as well. I work on our data analytics and data science, spatial analytics and data science team. So I work sort of on the far left of this graphic on AI tools and models and related geospatial analytic tools. I think it's important to talk about those first, because that's really that's where the work gets done, right? As he was just talking about. There's an AI assistant component to that sits on top of it that sort of improves our productivity, and then the agentic aspect of it, which is sort of how we're going to get more advanced work done in the future. So that GeoAI or analytics part of it has several components. It supports a lot of different data types, a lot of different workflows. And when I say data types, I mean not just imagery in this case, but also full motion video, LiDAR data, and other things can also be used with AI tools. Feature extraction, change detection, similarity search, all these things that we want to ask information about imagery. We support a lot of pre-trained embedded models in our system. These are models developed by other people, as well as models developed by us, as well as new location embeddings that were recently released. Very briefly, there's a collection of pre-trained models. There's about 100 different models provided. These are pre-trained models for specific types of imagery, for specific locations. So like there's an Africa building detection with Sentinel, or there's a Sentinel land cover global model, or other things, right? That's been there for about 5 years. The way that things are going now is more toward foundation models, as he was just mentioning. So we released a couple of foundation models last week. One of those is focused on geodemographics. So this is more demographic data and population data and economic data for asking geospatial questions. And then a geospatial vision language model, which is really sort of the new way to think about asking questions of imagery. And this is about asking human questions of imagery. Find me the whatever by layering an LLM model, a chat window, on top of the foundation model. So the problems that we had in the past of like, well, it was trained for this particular object or this particular satellite, go away. So by using something like a geospatial VLM, we can work with a range of image resolutions, a range of image platforms, and find many types of data. The piece that sits on top of that is the AI assistant. And this is really the thing that we're all familiar with and working in Google or in Microsoft or wherever, where there's always a little assistant to help us do things. So those things also exist in GIS software and imagery software. And in our particular case, those are models, assistants that are trained by humans, right? So our experts in particular pieces of our software help train those models in common tasks to make sure that we're promoting the most efficient or proper solution. And this is essentially just an LLM sitting on top of a generative AI model. So we can ask questions like, create a map for me where, I want to show the names of national parks, but don't include the word national parks on the end of it. Well, that would be a SQL query that you'd have to learn how to generate if you knew SQL. But instead, you can just type into a chat window that that's what you want to do, and it knows how to do it, just as an example. But what's more interesting is agents. So a geospatial agent is a special type of agent that is familiar with spatial concepts and principles of geography. And so we take this geospatial agent that sits on top of a foundation model, for example, with an LLM interface that allows us to create an autonomous agent that can perform tasks. And what's really exciting about that is those tasks can be chained together to solve larger tasks. There's sort of two ways to do that. You can just ignore the ArcGIS part on that. This is not ArcGIS specific. We can either take the geospatial component and through MCP use that in another agent, like if somebody through MCP wanted to use our geocoding or our other analytic tool inside their agent, or we can also take our tools and push that agentic capability into the geospatial analytics, right? So there's sort of two ways that that can go, and we encourage both. The end goal of that is to build agentic workflows and agentic mapping applications that actually solve problems so that we can create a chat interface that knows how to go out and solve problems, such as, go find a particular area in my city where the zoning has changed, build me a list of changed parcels by looking at imagery, where have I seen land cover change, generate a mailing list, I want to contact those people and things like this. And that was really fast. How am I down to?
Yeah.
2 more minutes? 4
Oh,
minutes
okay.
still? Oh, gosh.
All right.
All right, we'll go back to this one. No, I'm just kidding. I'll keep it short so we have time for Q&A. So the QR code is a longer version of some of the presentation that I just gave, about a 30-minute presentation about sort of everything that's been happening. It does not include information about the geospatial VLM and foundation model, which was just released, but we'll save time for the Q&A at the end.
Yeah. Thank you. So, next, Davis. Floor is yours.
Do you need a second for letting it sink? Hi. So yeah, I'll keep going. So I'm Davis from EPFL, and when Yifang invited me to come, I mean, I thought what would be a nice thing to talk about in this with this audience, and I kind of knew that there will be people talking about foundation models and VLMs. So I ruled that part of the things that we do in my lab. So I decided to go a little bit into the more applied part of what we do, because first I love working on that, on all kind of nature-based type of work, but also because of the urgency of the biodiversity crisis that we are currently living. So I don't know if this is something that you live in your everyday life or something that you care deeply about, but I do. It's the fact that biodiversity supports human living in a number of ways. It could be, in the way they help fighting diseases, by helping us developing medicines for food security, and you name it. I mean, the fact that we have various and thriving species makes that we can live on Earth. But to be thankful for all this gift from Earth that we receive, the thing that we are doing is that we are working our best to decimate and destroy biodiversity on Earth, and that's a fact. This is not conjectures, right? And so there have been a lot of actions by the international community. Typically, the 30 by 30 objectives, the Kunming-Montreal Global Biodiversity Framework, that aim at changing this trajectory in one where we preserve rather than destroy species on Earth. Of course, this all plays off in a very political, high-level decision-making world, but this is a high-level political world that needs evidence, and it's evidence that required mapping of the different species to know where they are and where they could be. And this is something that resonates with me because I've been working in remote sensing for a couple of decades now. And this is then, I mean, it led me to the point to say, okay, with geospatial data, maybe we can bring something to this edifice. And I know there is a bunch of such initiatives that look into like deforestation mapping at the global level and this type of things. And the direction that we started working on was how can we map species, and not just one at a time, but thousands, using all kinds of geospatial data and models that can go from very simple to very complex, like the ones that were presented early on. Okay, so let's play a game now. Let's see if you're up to date with your biology. So the question is easy, is on the screen. So how many species of trees we have on Earth? It's okay. You can just say something. It's fine. It's fun. 1,000. Okay. Who says
100,000.
100,000? Oh my God! Now we have a very, very wide range. 10,000. So, okay, so that's a logarithmic answer. I love it. I love it. Now, okay. So just that you know, there are roughly 73,000 species of trees on Earth. Okay. So this is the question that you could, you could use the agent and ask, and then the agent will go and fetch it for you. Now, another question is where these species are, and this starts to be a little bit more complicated because it relies on mapping, and it's something that we can support with our geospatial data. So that's an exercise we did 3 or 4 years ago. We basically went around looking of repositories for species observations. There is a lot around, and we found roughly 26 million observations for 10,000 different species. And then we started learning models that could map at the global scale where the species will be. The models were very simple. We were going with random forest and boosting trees, so we were very, very far from self-supervised learning and this type of things. But for a first idea, that was what we needed, and we ended up with a kind of a cartography of richness of species at the global scale. 10,000 out of 70,000, so it's not even the full picture, but that's what we can have with data that ecologists have been taking by their field campaigns all over the world. Okay, so we had this first map that we created about species richness, and we could have stopped here, but then we started to tried to think a little bit further on than just let's take pixels, let's take era 5 variables and try to learn a random forest. We then started to think, okay, we know where we are, but we want to know where the trees will be. And this could only go by interdisciplinary cooperation with climate scientists that helped us running climate models. And those climate models basically told us the global distribution of temperature, precipitation, humidity, 100 years from now over different scenarios. And thanks to this, we could modify our richness maps in a way that we are able to see which biome will gain in biodiversity, which one will lose, and provide this evidence of where we are going as a species ourselves if we keep doing the things that we are doing. And then even further. And here we have been starting to cross this data with the canopy temperature data to try to understand, given where species are and how much heat they can sustain, because every 3 species can sustain a different amount of temperature before the photosynthetic upper starts to break. And we could map spatially areas for which we exceed what we call a critical temperature, which means that beyond that temperature, the plant starts to die and cannot recover. And if you look at our projection 100 years from now, okay, 80 years from now, but we are moving from a 3% to a 15% type of regions that can go beyond this threshold of plants starting to die because of the excessive heat. Just let it sink for a second. Okay, so this is for me, it's a way to see how we can use geospatial data to map at scale, even with very simplistic models, distribution of species. And we're doing that for thousands of species at once. And this is where neural networks basically come in. Because the moment you are still working with traditional methods like Maxent, you're forced to map one species at a time. It means 10,000 models running in parallel. But with all kind of neural networks, foundation model-based models, we are now able to map multiple species with multiple sources of data. And like that, we have started to consider which type of data are the more useful. And for this, we could see that, and that's a good message also for the Tessera team, that if we have multiple sources of data, let it be climate, remote sensing, it can be radar, optical, you name it, soil data, their conjunction is what brings to the best results. So you can see in this study here, just the thing you need to see here is that the pink lines are the multimodal, so those that use multiple sources of data. So if you make a conjunction of different data, we get to the best results. So here is where I think all of us can work together. The ArcGIS team, the foundation model can be one of the inputs, and in a second I will show you how. So this is basically where we are now, and we are in a moment where we have the tools to make this type of conclusions, but then we are actually hitting the wall or having data that are poorly structured, that are missing sometimes. We are distributions that are non-stationary and things like that. So we started to consider that, and we came up with a model that could make sense of different sources of data that are not all grids. Okay, so this let's imagine we have data as vectors, are in the GIS world. It can be tensors, as in the Tessera world. It can be time series, and you name it. It can be text if you want. The moment you have a way to convert it into these vectors that we were talking about before with Tessera, you could do an embedding, that is not just based on image. It can be based on image and text at the same time. And this is where we get into like multimodal foundation models, and that's one first model that we proposed very recently with the work of Robin, with working in my team. And in this model called Maxent SDM, we were using different sources of data: images, climate, topography, location, text. And for the images, we were using subclip. I'm sorry, we were not using Tessera. It was not disclosed yet. And we were using masked modeling. Okay, and masked modeling is like in language models. In language model, you mask some words in the text and you try to predict them. And here we were masking some sources, and try to use a model with a reduced set of input. And what is the result of that? Is that you learn a model that is able to predict in the absence of modalities. So that if one day it is cloudy and you don't have Sentinel-2, it doesn't matter. If in a certain place you don't have a text describing a place, it doesn't matter, because your model has learned to predict in absence of modalities. And at the inference time, since you have learned this, when you're missing out on modality, you just don't use it. So this is a model that is multimodal. It can take as an input different sources of data, and depending on what you have, it can predict. And it can lead to species distribution maps that are very close to something that is optimal. As you can see on the very far right, you have a map that is using all the data sources at once, but if you miss some, you then get results that are actually pretty close. So at the very left, you're using only temperature, so your map to describing the species of this plant is not very good, but the more modalities you use, you get closer to the actual observation that you can see in the bottom right. And this is it. And I was a little bit fast, and I tend not to breathe between words, and that's just me, sorry. But now think of all the things that you can do with this. You can start to imagine embeddings that are based on all the types of data you can lay your hands on, and that's very exciting. Thank you very much.
Thank you very much, Davis. And also for saving quite a lot of time. So
Oh, no, it was. I saw the times up. I saw the times up sheet.
yes, it's help to save time. But Andrea, the floor is yours.
Okay, so then I will continue, and now I will focus a bit on how we can benchmark this geospatial foundation model that we heard during the first presentations, and how we can do this, and what are the limitations on benchmarking geospatial foundation model. I think we already learned basically what is a geospatial foundation model in the previous presentation. So it's a model trained on massive data that we want to use to solve some specific task after we prepare this model. So I'm going to be quite fast here. And what is the situation out there of geospatial foundation model? These were introduced probably less than 5 years ago. And this is the situation now of the trend in geospatial foundation model. So basically, in 2024, we release 3 models per month. Okay, so that's a lot of models to understand. So how we can understand if these models are working or not? Be careful, the last bar here in 2025 is only partial data. So it's not that we have less in 2025, we will have more probably, but this is the data up to half of 25. So that's the situation. We have a lot of geospatial foundation model. We have different type of geospatial foundation model. We heard about vision language model, the vision foundation model, task-specific agentic AI, some specific model for specific application, like species modeling could be one. And so it's a kind of a jungle, okay? So it's a lot of models out there, and we need to understand how they works and what are the limitations of all these models. So, and to assess this model, we want to develop some benchmarking task, some establish some protocols that can we follow to assess this model. Might be that some protocols are valid only for some types of model, only vision model or vision language model, but we need protocols in some way to properly assess this model. In the first years of this development, there were a lot of dataset used to assess this model. Some of them were the first dataset developed, like Aerosat, that it was an image classification dataset. It's a very easy dataset right now. All the model will reach probably 99% of accuracy on that dataset. So in some way, we solve it. We need to move to another task, a more complicated task that is up to the standard of the foundation model that are out there. And we start to do some work. Now this is 2 years half back, and we call it Pangea. It's a framework to assess foundation model. In this graph, you see we pick up a lot of different models that were available out there. That's, let me call it, the first generation of geospatial foundation model that were trained using different satellite data from Sentinel-1, Sentinel-2 to very resolution image and other sensor. And we try to define a set of tasks that this model should be able to solve. And then could be urban mapping, forest monitoring, disaster response, marine monitoring, and so on, crops. And then we ran some experiment. Our main goal was to try to understand from an unbiased point of view, because we were not the developer of these models, we were the user of this model. Are they working as they should? And we did this work, and it was not me, it was a big team of especially young researchers. Most of them are PhD students in KTH, Q Leuven, and EGN. And we worked together to try to define the task, which tasks are significant, if the labels of this task were reliable to assess the model or not. And we did some experimentation. So, and it was just a collaborative work among all this team. We tried to cover as much as possible the entire globe. And as you can see from this image, we failed. Why we failed? Because it's very difficult to find reliable data in some specific country or some specific area of the world. So we did our best to try to spread the data all over the earth. Not easy task. We ran a bunch of experiments at the time, and we compare all these geospatial foundation models. And the findings were that the first generation of geospatial foundation model, they were not really far away from a fully supervised baseline, and also with a limited amount of labels. So basically, the first generation were interesting first development, but still not probably reliable enough for a large use of this geospatial foundation model. So we, in some way, compare the performance of the geospatial foundation model with standard baseline, like a standard unit, was performing still quite close to the more complicated foundation models. And we highlight some gaps, especially the geographic bias gaps, and also the importance to have the multimodal and multitemporal task that needs to be in the assessment of these models. So we, in some way, run this framework. This framework is kind of growing, so it's not, that was the first experiment, but we have a repository in GitHub. You will have the QR code to the access. It was used for different new foundation models to assess the performance, especially from some model from IBM, from ESA, and from other research group around the globe. And it's growing, so we add some new task to the benchmark, and we are continuously trying to update the benchmark with new tasks. And that's the idea of evolving this, but we are not enough, basically. So the main problem is that there is a lot of possible ways of assessing this geospatial foundation model. It's an open research question, and we have to develop these protocols. So we really need like a larger community to try to address these challenges. And the main goal is to really also drive the development of this foundation model. Because if you start to optimize the model to the wrong benchmark or to the wrong task, we will just improve the performance of the model for something that is not really meaningful for the main user of this model. So in some way, my kind of end of this presentation is to search for help. We need help from not only researcher in machine learning, we need help from the user of this geospatial foundation model and how they can be used in a real world application where we can find more reliable ground truth data, especially in the countries where we have a lack of data, and also from a policy point of view, how this model can be used for solving our more pressing challenges. And just to mention the next steps in some way, so we are trying to add new data set, and when we add new data set, we also try to launch new data challenge. This is one recent data challenge that we launched. If I can briefly introduce at the beginning, it's called Reaching New Heights with the Geospatial Foundation Model. It's a challenge that aims to retrieve both land cover classification and height estimation for both vegetation and urban area. Is using also Tessera embeddings, Alpha Earth embeddings, and other two foundational models, TerraMine and Tor embeddings. And we asked the community to try to see how we can also merge different geospatial foundation model to solve this task of this multi-regression task of height and land cover classification. And I think that's it. So thank you.
Thank you very much. Can we move forward to the next slide?
Yes.
Yeah, thanks. So now it's a Q&A and panel discussion. So questions for our speakers, we didn't do the right after presentation question. Okay, Chef, I have a question for you. With Tessera, what's the next step? Do you have a Tessera version 2 in the pipeline?
Yeah. Thanks, Ivan. Yes, we have a couple of ideas. So one is, so those people using Tessera may have noticed some artifacts in there. So we're removing the artifacts and also regenerating for all years and all regions for 9 years since Sentinel-2. So that's happening. We're calling it version 1.1. And then with version 2, we are actually trying to scale up by putting more data, bigger models to see where the scaling loss can help us. So that's sort of more of an ML-oriented work. And then we have quite a few other research projects. One particular one I'll mention is just trying to do uncertainty quantification using attentive neural processes. And if you're interested in that kind of thing, I'm happy to talk more about that. But trying to say where we don't have ground truth data, what can we say is the truth? So if you don't know, for example, tree height in a particular location because you don't have ground truth, how can we interpolate between known tree heights using Tessera and attentive neural processes? So that's some work that we've just started, which it looks very promising.
Yeah, thank you. Yeah, please.
Yeah, thank you for this really interesting presentations. I would wish that Franz Imler would have been here, who was this morning questioning a bit about the EO use, AI use here in the different work program activities. But that's also then pointing to my question, because this is very, very interesting and great work. And you mentioned, Yifang, already the link for forest fire mapping, for example. There's an activity now also in the work program, GWIS, that does exactly that. In your group, how do you assure that all the research you are doing is then also linked with the Geo Work Program activity, so that we can take stock of all the developments that you are doing?
Yeah, that's actually a very excellent question. I think it's really important to keep all the communication channels open. So what we've been trying to reach out is more to Geo admin to say, okay, can we be part of the knowledge hub? And then now we have a community page. So then we can put, our models, the open access data sets, models collected by the community, the efforts like Living Book, we can put it there. That's accessible to everyone. That's one thing. And we also want to reach out to, the flagship initiatives or, the commoners to see, how we can work together. I think what are the needs? That will be the next step to say, okay, what are the needs from the user community? I mean, you're expert, let's say, on urban. Then what is the urgent need for the urban community or for the biodiversity community? So that then we can actually say, okay, we maybe have a focused target for a period, tackle those challenges. Yeah, thank you. Good question. Yes, please.
I have a question about the need for this ground truth data in terms of in situ data, because I think maybe in terms also of this biodiversity mapping, because now I think you're feeding your model with everything you can find. But I was thinking if you were to take the opposite, so, okay, if you could pick one ingredient for your model, is it a thermal threshold or is it the exact location of trees? What would it be that would improve your model drastically so that we could prioritize collection of data? So that, if there was something like, I don't know, 3 variables that you really needed, what would it be?
It's funny that you asked that, because in a way we've been I've been living in a world where the band importance was what I was always asked for, and then we got hit by all this. Okay, now we have the technology to explore, right? So the model that I presented allows you exactly to do that. So it's something that will, if you give a number of inputs, is able to rank those that are of highest importance, because you can mask them one by one and see what is the difference in performance, for example. And since you do it only at inference time, but that becomes extremely fast. Now, I think that in the case of the species distribution model, there is no real satisfactory answer, because every species has different needs. Species that are mobile will need some variable. Species that are sedentary will need some others. The scale will change by every species. So I think it's almost, in my opinion, it's more important to have an approach that allows you to focus on the right one, since you can have them all in the model, just to be able to pick. So you need an approach that is able to help you choosing, rather than trying to decide a priori something that will work for everything. Does that answer?
Yes, I'm just thinking,
Cool.
Is there a way to document those? So like test it and say, okay, this is really what we need. That's key, so that we can also try to get and collect those things. So prioritizing something and then having a list, the wish list of, you go find them.
But you mean the species you want to document?
No. So let's say if they were, let's say in the end, it's funding. You pay to go collect some sort of data.
Yes.
And so could we develop a list of variables that we could prioritize to go and get? I understand, I mean, you cannot do it for every single species, but maybe, I mean, you need to prioritize or decimate, your variables.
Right,
But
right.
if there was a way for us, because I'm working on this geospatial requirement database, and now I think, okay, well, what could we give to AI? Are there some variables that we should already put in our list so that people who go collect them
Yeah,
would
yeah.
have them on there. Okay, that's the return on this collection. So that's
Right,
terrific.
right. Yeah, truth is that we were focusing on variables that are collected anyway. So satellite data, distance to road, because we have the maps of the roads and things like that. If we were to ask for specific types of data, it would be very interesting to run them in the model, see if they're useful, and then recommend. Yeah.
Maybe I can answer that here because the answer depends on the task that you want to do, because the ground truth is only used for task-specific training, because that's what the labels are for task-specific training. So what we have done, and this is work I didn't talk about, is that we can do something called active learning with uncertainty quantification. So what that means is that, let's say I have a particular task, whatever it is, I can then use something like Tessera or a foundation model to say, these are the places where I have the most uncertainty in the quantities. Now, those may be areas you don't care about. For example, there may be huge uncertainty in Antarctica and you don't really care about it. But if you find a location which has uncertainty, but it's something that you want to know better, then we can point you to, this is the place where you should do a data collection expedition. So this is something we are actively looking at ourselves. And I can tell you more about it, but there is a principled approach to being able to reduce the uncertainty for specific tasks based on the work that we've done.
Thank you.
I'll say thank you for the work you're doing. We steal it and then we reinforce learn it, or 50 centimeter, 30 centimeter data, and then apply it over vast areas. So we're extremely grateful for the foundation models. But also to speak into that question, what we quite often will be doing, Jonathan Hendry, Fourth Intelligence, we tend to work at kind of regional or national scale projects, very high resolution focused. And what we tend to do is we'll use exactly these models, the foundation models, to understand, 30 classes of ecosystem, for example, and try and understand that. But then we'll, from that, be able to gain an uncertainty. And then we send teams out into the field and ask for acoustic harmonics, or we'll ask for eDNA. And then we can understand species density, different species that are in that ecosystem, and then retrain the model in different ways often, to then have a fantastic model that's then delivered to a client that then goes into Global Ecosystem Atlas and various other kind of solutions. So I just wanted to jump in as well as say thank you for the work you're doing. You'll never hear about it, but it's hugely, hugely valued by us in the private sector. I was also going to quickly say the CEOS paper does actually mention geo explicitly, so it really would be worth looking at and potentially commenting on, or if they do a re-release, it mentions a lot of the programs.
Okay, yeah, thank you for your comments and also the remark about geo. geo is a big organization with many member states, partners. Since we just finished the living book like a couple of days ago, it has not been thoroughly examined by GL. So that's why every author put their names behind the chapters. So GL is not responsible for what we say. But only in my introduction, I mentioned that we are one of the GL initially, but this is a community effort. But when this has been independently reviewed, then GL will put a stamp on it. But for the moment, it's a community effort. Yeah. Please.
Yeah, a question around Tessera. I've been using Tessera for classification. It's definitely very good. For other tasks I'm doing, for example, crop yield forecasting, the situation is that you are near real time, you are halfway through the season, and you want to estimate. So basically what you want is that the embedding tells you of what happened through the season so far, and not so back in time. How do you see the evolution on this?
Yeah, this is a question that comes up all the time because it's annual embedding. People would love to have sub-annual or harvest time embedding, sub-seasonal embeddings. Two reasons we didn't do it. One is that in cloudy regions, we don't get that many readings at all. So if you're in Gabon or in Indonesia, parts of the Amazon, we get almost no readings for several months at a time. So we decided at a global level to look at annual, and also at 240 terabytes. If you do sub-seasonal, we're multiplying. Let's say you do 4 a year, you're going to talk about petabyte a year, which is it's basically unaffordable for academic institutions anyway. However, The one task we are looking at is using some advanced techniques. I'm happy to tell you, but basically using some wavelet basis functions to create subsets or even daily equivalents of embeddings. And this is very advanced research at the moment, not really anything that I can talk about because I don't know how well it works, but we are very keenly aware of the problem. This is something that we'd like to solve.
Thank you. And any other?
Yeah, thank you. I think it's a great topics for the AI4EO. I do have questions to Davis. And yeah, it's very interesting to use the AI model and even to the geofoundation model into the species distribution. But I also, on the other hand, considering for the limit or capacity of the EO data, because when we say species can have the multi-layered like say forestry trees species you mentioned. Even we look outside, they have the big trees, there are some shaded trees. But from EO data, we see from the top, we get the good observation from the top, but for the trees beyond, maybe we need to some forestry or ecological information considering environment. But still, can we go beyond the limit of the EO data, or from this kind of geofoundation model, we can bring more information together and then to make the real happen? Thank you.
I think this is an excellent comment, and it really pushes towards this multimodal type of foundation models, because the models I presented, they don't rely only on remote sensing data. And you're right, with remote sensing data, you see only the top of the canopy. But if you have information about soil, about climate, about all type of things, and you can make a distribution model that has been trained on data that is based on field surveys, the plants that are located by field surveys or by citizen science initiatives are not only based on what you see on remote sensing data. Nobody has been ground truthing on a satellite data, right? This is like field experiments. So if a tree is below the canopy, it's still recorded, right?
Yes, but you also mentioned for the distribution also as a critical thing. We also, so for considering for the detailed spatial distribution, we definitely need to rely on remote sensing somehow.
Yeah, but not only. That's the point.
Yeah, that's good. Thank you.
I can answer that. So, I mean, it is true that JEDI structural form is going in the, the second return is from the understory structure. And so you can actually use JEDI plus foundation model for doing interpolations of the structure. So we can do that. Plus, GBIF or iNaturalist is reasonably well geolocated. And so you can get citizen science type inputs at scale. So nobody's done it as far as I know, but you could use iNaturalist / GBIF plus JEDI and foundation model interpolation to do some of the things that you want to do in the understory.
Yes, yeah, thank you. Yeah, definitely we can, after considering the multimodal remote sensing data, then yeah, can consider, but also need to consider for the structure information, also the species related. Thank you.
You have to pay for licenses, right? So for the global south, if they want to use your agentic AI assistants, and I mean, do you have a discount or open access to our geo members in those regions? And also, like if the models are trained, maybe it's the data from global north, so would it work well in the global south?
Good questions. So there's two questions really. One is about software. The other is about training. So on the software access issue, so there's a few different answers to that question. Yes, it is commercial software, but it's also software that's in use by, I don't know exactly what percentage, but well more than half of GEO members and participants. So most national governments and universities around the world already have it. Those who don't, there's a lot of discount programs, conservation grant programs, humanitarian grant programs, development programs, and a lot of other ways. If you want to know a cheap way to get the software, ask me, because I don't work in marketing and I'm happy to tell you. So, yeah, so and all of the AI work that we're doing is not like an additional license or an additional cost. It's just a thing that, as I was mentioning to you earlier, if you're a user of our software, it's something that your license administrator needs to turn on. So if you're like working at a university and you have a site license and you can't get the AI stuff to work on your network, it's probably because the license administrator at your university hasn't been told that you're allowed to use the AI stuff. So that's just an institutional protection that a lot of government agencies, universities, and others are like, hey, be careful about your use of AI. So we just leave it off by default, and somebody who administers your system just has to turn it on. It's just a checkbox, that's all. With regard to training, so a lot of our models, so the pre-trained models are very specific, right? And a lot of those have been developed for different parts of the world, and they're very clear where they were developed for and who developed them. So there's, we developed a building damage detection model that was, say, originally developed in North America that somebody adapted and made work in Africa, right? So it'd be tagged specifically to that. For the more recent work on the vision language model, for example, the first version of that, which was just released last week, is just RGB data, and most of the training of non-imagery stuff was US and Europe, because that's where we have the best data sets for objects that people might want to look for. Bridges, houses, trees, rivers, all these named objects that people want to look for. There's, 1 billion of those samples that went into the training, actually 1.65 billion, I think. We just grabbed what we have access to now. So over time, later this year, it'll be multispectral, it'll be trained on other parts of the world, and it'll continue to grow. But yeah, we try to be very transparent about that aspect of it. Yeah.
Maybe short answer.
In that case, the benchmark is only on the embedding part, so the one that is open released. So, and you cannot really go deeper in producing embeddings in other scenario because you don't have access to the weights in that case. So in that case, you can only benchmark the embeddings. That is still a challenging task because it's globally available like Tessera, and there are a lot of possible tasks that we can imagine with these embeddings to explore. So it's an open challenge to assess and understand the limitation and maybe develop the next Tessera or Tessera version 2. Yeah.
Yes, thanks. We're almost finished, but I want to ask each panel member to give like a
So I think from a very high level perspective, what we're seeing is the acquisition of very large amounts of data from remote sensing. From the number of satellite launches has gone up from about 30 a year to about 3,000 a year. So there's a tremendous influx of data. At the same time, we have the large proliferation of data centers, which means you can compute things, and the proliferation of deep learning and AI tools. So these trends are basically unstoppable. Nobody's going to stop collecting data from satellites. Nobody's going to stop developing more AI models. So the joint value from AI plus EO and using it for solving critical problems that facing humanity is basically such a opportunity that comes once in a lifetime. So I think it's only going to get better.
Thank you. Thank you, Andrea. Do we complete?
Yes, I mean, I completely agree that we are in a really, really golden area of data and models. So we definitely have a lot of opportunity, and probably now we should find a path to reach all this opportunity that I think are still not developed yet. We can solve a lot of challenge that we had in remote sensing in other disciplines that can be addressed with this new technology in some way, especially basically using the self-supervised learning framework. We can really unlock some challenges that were impossible to solve a few years back. So I think it's a very exciting era for remote sensing and EO data, where AI will definitely play a role, is already playing a big role.
Thank you, David.
I would say don't lock out domain specialists when you develop. Co-develop, include physics, include domain laws, and try to create new science and new laws that they are currently unknown. For me, that's the real frontier.
I think as somebody who's been around remote sensing since Fortran, I think I'm not the only one in the room, by the way, I'm sure. I think, where things have sort of started to show up in the last year or so and improving with laying LLMs on top of foundation models and development of vision language models with a geospatial context is really exciting, particularly with there being a lot of different models and evaluation of models. Competition improves quality, right? Everybody's going to want to be better at something, right? So it's good that there's not just one. But I think where things are going to be, say, 2 years, 3 years from now, is that most of our users in geo work programs who aren't thinking specifically about AI are going to be able to make greater use of EO data because they won't need all of the imagery expertise in order to get a useful answer, right? You don't actually need to understand pixel science. You just need to understand your domain science and know what the right question is to ask. Probably ought to be able to recognize when the answer is really wrong, because the model's not always going to be perfect. But I think there's a lot of potential for the use and uptake of EO problem solving with AI is just going to see a lot of growth.
Thank you very much for your comment. With all the comments, I think some time ago I saw a presentation that is only 10% of EO data or the information generally being used for decision making. So we hope with this Earth intelligence for all the AI help with generating useful information and also with all the community effort, there will be really a lot of uptake use of EO data in all kinds of local to regional to global decision making. So thank you very much for your participation in the session, and thank you to our panel again. Big applause to everyone.